Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. So today we are going to deal with a new topic which is basically related to the self attention mechanism, right? So let's read the question first. The string ABC in domain English is the string alpha, beta, gamma in domain Greek. Show the self-attention separately between English input sequence ABC and between the Greek input sequence alpha, beta, gamma for each of the cases. Show the attention values and conversion to output values using the attention. After applying self-attention, also show the cross attention and corresponding values. So there are some technical terms, we will go through them one by one. So first we see that there is this translation which is occurring between the English alphabets and the Greek alphabets. So the idea is to transform each character into its separate vectorized format. What do I mean by that is each character will be represented by its corresponding vector from the word to vector table which we have here, right? So we'll see how that goes. So before that, what we also want to look at is the architecture of transformers. So it was initially presented by Google researchers and we'll get a look at it. So the first part of this one is basically put the input characters here with the input embedding. So embeddings are kind of word to vectors that we'll see, and then it is added to the positional encoding. Once done, it is then handed over to the next section in transformer, which is multi-head attention. Now this multi-head attention is basically doing the calculations or matrix multiplications that we'll see in the below steps. Then the next step is basically add and normalization. Throughout the diagram we'll see that in many steps transformers undergo repetitive addition and normalization in order to keep the scale factor of the numbers in check. Next, the feed forward mechanism for the neural network, and finally again add and normalization, right? Once this is done, what we also want to look at is the output from this one is then flown into the input of the next portion of the attention mechanism. So for that, what we have given is the output shifted right. So in our case it is alpha, beta, gamma. So it is given to the output embedding, again the word to vector table. Then once it is there, again we add it to the positional encoding. Now this time it is masked. So we see that this one has masked multi-head attention instead of multi-head attention. So it is because we want to ensure that when generating a sequence, each token only attends to the previous tokens in the sequence, meaning that we are not allowing the future tokens. So meaning when we are at alpha, beta, gamma, we don't allow it to basically know that after alpha there is a term called beta, right, which is the next thing in line. So future information leakage is prevented by using masked multi-head attention and basically allowing for sequential generation of text, which we see in ChatGPT. Now one more thing which we need to keep in mind is this particular portion, this one is also called the encoder part of the transformer, and this one is called the decoder part of the transformer, right? Similarly, after masked multi-head attention calculation, we send one of the input parameters from the output into multi-head attention and 2 from the actual input that we got as A, B and C. Again we perform multi-head attention, add, normalize, again feed forward in the neural network, and then finally we get into the linear format of the vectors that we want as output and put Softmax into it so that we get exact mapping of whether alpha is most suited to represent A, B or C. So that's a brief outline about transformers. I know this is a big topic in itself, but that should work with the problem that we are dealing with right now. Now let's go to the actual problem. So we have this English input sequence ABC and the Greek input sequence alpha, beta, gamma. So step 1 is like the word to vector table which we had above. So if we go back, we see that this is the table itself, right? Each letter, let's say A, is consisting of a 1 cross 4 vector, 1 row and 4 columns. Similarly B, C, this length varies according to the problem. And when we say about parameters, so the number of such parameters and their complexity is what basically defined in like 70 billion parameters, 30 billion parameters and so on. Now the first thing that comes to observation is this particular encoding needs to be done for both input sequence as well as output sequence, right? Basically for output sequence, what I have denoted in the problem is rename it as Greek input, because basically in translation, if we are trying to map these two, then both of these are kind of inputs to the transformer or to the self attention mechanism machine. Next is we see that we have positional encoding table that has 5 rows, but you can see that in reality we have only 3 tokens A, B, C and alpha, beta, gamma in itself, right? So 3 encodings would have done, but this is not the case because there also exist start of sentence and end of sentence characters. So when we say ABC and send it to the self attention, there is also a start of sequence and an end of sequence character. Similarly with the Greek sequence as well, right? And since its word to vec encoding is not given, we will take it as 0. But most likely what will happen is in practical scenarios, there will be a separate word to vec for the characters that represent start of sequence as well as end of sequence, right? So we see that positional encoding has 5 rows instead of 3, right? So now we will try to add positional vectors to the vector embeddings. So this is the vector embeddings that we have calculated in the previous step. As stated, the start of sequence is 0 as well as the end of sequence, and we just simply add it. So the obtained dimension of x will be 5 cross 4 to find x dash for alpha, beta, gamma. Then x dash will also have the same dimension, which is 5 cross 4. Next we move to step 4, which is calculate queries, keys and values. So if we go in the question, we see we have got 3 matrices: key weights, value weights and query weights, right? So the step will involve for each sequence we need to find query matrix, which is again going to be 5 cross 4, and it is going to be x multiplied with wq. So we see that these are conformable matrices. From memory it is x going to be 5 cross 4 and this one is 4 cross 4. If we check it on the question, so you can see that it is 4 cross 4 matrix all the way, right? So then similarly we can calculate k, which is the key matrix and the value matrix, right? All these will be calculated for A, B, C, that is on x, as well as on alpha, beta, gamma sequence, which is x dash. So in total we will get 6 matrices at the end of this step. Now this is very important that we get to this state. Alright, next step 5, which is compute self attention. So for that, for each sequence, that is ABC and alpha, beta, gamma, we will compute the self attention score. So it is basically this formula which tells query matrix, which we calculated in step 4, times k transpose over square root of dk. Now we will understand all these terms one by one. Q and kt are conformable because q has 5 cross 4 and kt is 4 cross 5 because k was 5 cross 4, right? So this will result in a matrix of 5 cross 5, right? Next, dk. So dk is a new term. It will be the dimensionality of the key matrix. So in our case it will be 4, just as we saw above in the question. By now we've got two 5 cross 5 matrices from both sequence representing their attention scores, right? Next, we move to understanding the 5 cross 5 matrix that we obtain. What does this mean? Attention and score, what does this mean? So we'll understand the structure first. The rows in the 5 cross 5 matrix that we have obtained basically represent the query token positions. Example for each token. So let's take an example. For each token in the input sequence, we'll have a query token in that respective position in the matrix. Next, the columns represent the key token positions. So the rows were representing the query token positions and the columns of the matrix will represent the key token positions, and each key token will have its separate contribution for all tokens in that query. So if we try to put it in more simple terms, each entry of Aij, that is the elements of the matrix, represent how much the ith query or attends to the jth key token. Now ith query represents each query token in a row and their attention to the jth key token in that particular column. Now this can be a little tricky, but I'll rather suggest you to think about it in a matrix format, that each row and each column will meet at a point, and this point basically marks the attention score for this query token with respect to this key token. Alright, next we move to application of row wise softmax to the attention score matrix. So for each row correspond to a particular query token, softmax is applied across all columns. So we take a row and then we apply softmax to the entire row. Next, mathematically what we can figure out is softmax will be equal to exponential of Sij over summation of k equals 1 over n exponential of Sik. So by this we can understand that Sij is basically the score at position ij, which I just explained above, and n being the total number of tokens. So in this case it will be 5, since we had SOS as well as EOS at the start and the end respectively. Next, a very important observation, which is each row after this particular calculation represents how much attention the ith query token gives to each query tokens. Before it was a query token to its respective key token, but now it's changed for ith query token to all the query tokens submitted. So what we get here as the output is basically a 5 cross 5 normalized matrix whose each row sums up to 1, because we have applied softmax right now, and this will be used to calculate the weighted sum of the value vectors, which we will see down below. So if we look at it, the mathematical representation will be output for self attention equals softmax of attention score, which we just calculated above, and that will be a 5 cross 5 matrix, and it will be multiplied to the value matrix, which is 5 cross 4 in dimensions. Now if that is multiplied, the result will be 5 cross 4, right? So as with all steps, this one is no exception, and we'll get two matrices of 5 cross 4 dimension from both the sequences, right? Next, the last step which we want to do is the cross attention computation. So basically what we try to do is the same step what we did just now, but use the queries from one domain, let's say English, and use the keys or values from the other sequence, which is Greek. So the process will be same as we applied for self attention. So only change that we'll have is, let's say Q will be from English and K raised to power T will be from Greek, right? And dimensionality of K will remain the same, which is dk, and it will be 4. So that is how we calculate cross attention and self attention for two given sequences using the transformer architecture discussed above. So that's been it. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.